So today we're gonna continue our last week's lectures on quantum optics, and we're gonna cover primarily single mode squeezing, all right? And hopefully we'll get to the GRA experiment, and we'll be done. Last week, I told you that you could think of a field as an harmonic oscillator, right? And when you have a field, actually two fields, two harmonic oscillator, and there is so what was the picture last week? So it was like this. It breaks into two photons, two low. And so I said we have a higher energy pump photon. So high energy. And this is low energy. It breaks into two low energy photons, right? Low energy, low energy. Correct, remember? And this process, what's going on here in the BBO crystal, is called parametric excitation. Yeah. And I told you that this parametric excitation process is very similar to an excitation of an harmonic oscillator, right? Okay. Today I want to start a lecture with just give you a little more details on how this process goes. So I'm going to start with the wave equation. Okay. So we know wave equations are like this in free space, correct? All right. In the media, does anyone know how does the wave equation changes? Yeah, in the media, like in the material. We know that light slows down in the media, right? So that should reflect on the wave equation. Right, yeah, something changes here. Okay, because you know that C is equal to this, right? So it might be natural. Of course, there's a more formal derivation behind it, but you might expect that in the material, the velocity of that light is changed to this with the same form, but just the constant become different. This is called the vacuum susceptibility, and this is the vacuum permeability, right? In the material, we have the induced dipole, induced electrical dipole, and an induced magnetic dipole. So, so those the effects from those induced dipoles comes in to here. They changes the constant, and thus change the velocity of the wave. Yep. All right. So let's change this to wave in the media. So wave in the media looks like this. The effect of the dipole-induced response, all that is included in this constants. Okay? Now, to be more specific, how does that happen? We know that the dipole are the linearly induced dipole are like this, right? Last week we talked about this. All right, but if we want to, okay, so basically, this is the new constant, okay? Now, if we rewrite this, I'm kind of doing this backward, but I think it's easier to understand this way. So, so say we don't have induced magnetic dipole in our material. Our material is basically non-magnetic, so it doesn't do anything magnetically. So then we'll just keep the vacuum permeability constant, and then we will just use this. But now let us replace this by P. Yeah. So you combine this constant with E, just like you do here, and that's a P, right? Okay. This is actually a more general form. All right. This is a more general form, and it can be derived if you know what this is. This is the so-called vacuum. This is called the displacement. And in the media, the Maxwell equation should be rewritten with D and H. Okay, if you don't know what this is, that's okay. We don't need to worry too much about it. But I'm just saying, I just want to let you know that this is actually a more general form of the wave equation in both vacuum and media. Okay, and it is derived from this. But let me continue. This is more general. Why is it more general? Because when the material respond to the electric field nonlinearly, we can still use this. Okay, so let's just take this as our starting point, and let's write again P in a more general form. E to actually yeah, this is kind of stupid. I'm just keep it. Okay. Okay, let me expand it to the third order. These are the second and third order are the most important nonlinear effect in optics. This gives rise to the Pockels effect and second harmonic generation, and this gives rise to the so-called curl effect. Okay, so that's a more advanced topics in nonlinear optics. You don't need to worry about it, but I just wanted to let you know that this can have many higher order terms, as high as possible, as high as you want, because this has to do with, like, remember we talked about this last time. This has to do with the lattice, like how the electron move in the system, right? If it's moved just slightly, then it's basically experiencing the harmonic potential. If it's moved further, then we'll start to sense the lattice, right? And the more you move, the further you move, the more you sense the lattice. So the lattice structure will comes in a higher order process. Okay. Now I just want to briefly say that so these are all vector equations, by the way. So I just want to briefly say that it is not hard to understand the linear response, right? Basically, it is just the induced dipole moment following a field linearly, right? So there's just a constant, and the vectors are the same. If you have a field oscillating like this, your induced dipole will be sure oscillating like this. It will be oscillating in the same direction, just like a current driven by a field. But in the higher order nonlinear process, it's no longer so. Okay, the induced dipole moment does not have to have the same direction as the incoming fields. Okay, so I mean, this is kind of obvious from the form, because here, the first term we have a vector, right? So that means the field is important. In the second term, we will have two vectors. how do you combine two vectors to make another vector? Well, you can do like outer product, you can do stuff like that, but it's kind of absurd to do outer product between two E field. There's no really good reason for it, right? So you can kind of expect that this thing, that whatever is in the front, will have to give the vector characteristics to the dipoles. Okay. As a matter of fact, this is a tensor, something so-called tensor, polarization tensor. Okay. And how tensor work? Well, it's all very complicated. Even I get very confused. But basically, it works in such a way that with every combination, so you take a E here, you take a E here, you take a component here, you take a component here, right? Whatever combination you have, there is a coefficient. Let me just call it J and K. There's a coefficient for it. There's a coefficient corresponding to this. So for example, so if I label the E field X and Y component, X, Y, Z component as 1, 2, 3, then, so say, if I take the X component of E1 of the first field, let me just call A, and the second component of the second field, or this could be the pump field, it doesn't matter, okay? So this is the X and this is the Y. So there will be a corresponding coefficient, nonlinear coefficient for that, okay? And this, and for every, so P1, P2, P3, so this is the X, Y, Z component of the polarization. For every polarization, it does this. It does this. Therefore, there is another index here. So you see? So it's basically all combinations of the E field will contribute to the first element of the polarization in a certain way. And all combination of the E field will contribute to the second element of the polarization in a certain way. So how many combinations we have here? Here we have 3 times 3, we have 9, right? For each component, we have 9 elements contributing to this. 9 elements contributing to this, 9 elements contributing to this. In total, there are 3 times 3 times 3, 27. 27 components. So let me just put I here. So there are 3 times 3 times 3, 27 components. And that's called tensor. It's very complicated because there are so many elements. Okay. In terms of matrix operation, you can define a way to do matrix operation to like if you want, of course you don't compute this by hand, you just use your computers. And of course you can define a certain metric operation to perform such an operation, but I'm not gonna go into detail. I'm just gonna say that in general, this is a very big number, a 27 element 3D matrix, okay? And together, they make a vector. And this is even worse. This is 3 by 3 by 3 by 3. So 3 to the 4th order. Okay, like 91 elements. 91 elements. So they're all very big. But under the most, in most cases, they are, I believe, only, there's like because there is a symmetry in the lattice, right? So it will respond to a certain combination a certain way. So out of these 23 elements, there's actually only like 2 or 3 unique numbers, and all others are identical to these 3 numbers, okay? So for the sake of our discussion, we're gonna assume that there's only one unique number, and all of them are the same number. Okay. So from this point on, we're gonna work with scalar. So we're gonna say we're gonna work with scalars, and this is whatever combination you have. We have all the same chi2. All right. Okay. So if we put this general form, oh, sorry. So let's transition to vector. E. Actually, I'm just going to write E squared and E third. Okay, so this is our simplification. Otherwise, it's become impossible to teach it. Let's put this back. Sorry. Okay. All right, you see that? So we just basically put this back here. This is just the that typical. So this basically is reflexive index of reflection. What is important is this term. Okay, so let's just put this back to what it is, and move this term to the other side. Oh, that good question. I ignored it. we could have chi3 here, but yes, thank you very much. We could have chi3 here, but I just want to demonstrate something. Also in chi3, for any higher order excitation, higher order nonlinearity. No, any nonlinear excitation is parametric excitation. Okay, so it will be sufficient to just explain parametric excitation using the second order. The math is the same for the third order too, and the fourth order and the fifth order. Okay, so it looks like this, right? All right. Now, this is, again, just like we had before. This describe field in the material. That's important. That's important. Field in the material, because the K changes in the material, right? Remember last time we said that it was impossible to match the K, match the momentum in this down conversion process if it's in the vacuum, right? Because the Kp, unless it's degenerate, but if it is not, then it's not possible. So that kind of reflects also here at this level of the equation. All right. The special thing about this equation is this term. Okay. This term is quite magical. Let me demonstrate it. So, and this is where the parametric process or parametric magic happens. It's basically a wave mixing process. But you will see that in a moment. Okay, so this, you see that this equation is basically very similar to, a source. So this, here you have a source term. Here you have the field term, like or wave term, like how your wave respond to a source, right? If you let's see. Okay, never mind. All right, so you see that this is also so this is of course derivative in space, and this is derivative in time. But you can see basically all dynamics is going to be in time. This is a partial derivative equation. So you can safely assume that if I want to see how a single mole respond to the drive, I can just separate my space dependence and my temporal dependence like this and put them here. And this will make this a k right, k squared so here I'm using, so this is the total field, and this is only the time dependence, so don't be confused. Okay, and I have, so this is a partial derivative, right? So I can take this out, e exponential ik x exponential ik x and eliminate all of them in each term. So you're left with this. Okay. Now this is 1 over v squared. This is 1 over c squared, right? So when you put this here, remember this is the wave vector in the material. So when you combine this with that, it becomes the frequency. The frequency doesn't change in the vacuum and in the material. So this is this. Okay. So in the material you have V times K. In the vacuum you have C times K naught. The frequency doesn't change. Okay. We're almost there. So this, throw it here. And this is V over C. V over C is 1 over n squared. Is it? Yes. 1 over n squared. Okay. Okay, we're getting there. Because what I want to show you is an equation of harmonic oscillator. All right, let me put this on one side and the other on the other side. Minus. Okay. Yep. That's our equation. So this is a very important equation in nonlinear optics. Okay, this tells you for a single mole, okay, single mole parametric excitation. Okay, so what you see here resembles an harmonic oscillator. Remember, we have how does it go? Like this. This is m. This is 2, and we have square minus x, right? No, or do we? Okay, yeah. Oh, we don't have this. Sorry. For a particle, harmonic oscillator has a form like this. We take n from both sides, so it has basically exactly the same form as the field, right? Right. On here, it is a drive. So this is a harmonic oscillator. Okay. Now, so this describe the dynamics of the total field. In the media, when you have P, when you have like 3 moles involved, your total field include 3 components. Correct? Now, oh sorry, got a square here. Yeah, I forgot the square here. I always forget the square. What else? Okay, I have the square. Square is important. Why is square important? Because the total field is this. The square gives you all combinations. Okay? We have, of course, this terms, right? And we have other terms. How many unique combinations do we have? 1, 2, and 2 are not the same. 6 unique combinations. In total, we have 9 cross terms. Correct? Okay, let's try. 1, 2. Yeah? This is 1, 2. 1p. Yeah? 2, 2, 1 we already have. 2, 2 we have here. 2p. Right? P1 we have. P2 we have. PP we have. Okay, so only 3 unique combinations, and of course you have the coefficients in front. Okay? Now, what I want to emphasize is, remember we okay. All right, and also here we're gonna have 3 terms, E1, E2, E3. So these are linear terms, E1, E2, and E3. So in total we have, and that's, since the pump is strong, we will assume that it does not change, okay? Through this term, of course, we know the energy is converted from the pump to the other fields. But for now, I'm gonna assume that we have such a strong pump that it does not deplete. Okay, it's like a big gas tank, and you only fill it with, you only like take a small cup from it, right? All right, so we have 2 equations. Oh, I'm sorry. This is not single mole. This is actually, this can work with even 2 modes. So two equations, the corresponding oscillating term here, right? Now what is important is here. What do we write here? Of course, we're going to write all 9 terms. Oh, right, you're right. There are 6 cross terms. In total, 9 terms, 6 cross terms, and 6, 3 same terms, right? And out of the 6, there are 3 unique ones, okay, because of the interchangeability. All right, so in principle, we're gonna write all 9 of them here.
What do you mean 9? I see only 6 terms.
Actually, two. You're right. 6 terms.
Okay.
All 6 terms, because they are the same. So we're gonna, in principle, we're gonna rewrite all 6 terms here. Yes. So this equation can be rewritten. So if you wanna, and of course you can also, you don't. So this is 2 mole. If you want, so these are the 2 mole. If you want to discuss 2 mole parametric excitation, you do this. 2 mole and a pump. If you want to do 1 mole, you can do that too. 1 mole and a pump. Single mole. Okay? In this case, we have the degenerate excitation, the degenerate case where you have same color, same mode, same direction, like we discussed last time in our quiz. But here we're gonna do 2 mole because this is more general. You can make one of them 1, then it becomes 1 mole. Okay, so let's do 2 mole. Can we do 3 mole? Not really. Yeah, you will see as I work out this part that this is where the magic comes from. Okay, so as we put in these terms there, you see that this is a nonlinear equation, right? And it's very difficult to solve nonlinear equations unless you do it numerically. To do it analytically, probably not possible. It doesn't have a closed form solution. So what we can do, the next best thing we can do is to use the perturbation approach. Perturbation approach will give us not the full answer, but the answer it gives us will be sufficient qualitatively. It'll give us a qualitative it'll give us the qualitative behavior of the system, but the quantitative, the exact quantitative value you have to solve with computers. Got it? Okay. So we're gonna use a perturbative approach. Let me rewrite this. Let me just use one of the mole to demonstrate how this works. Okay, still a lot. Okay, so this is how you do perturbation. So you just basically have first order, and you denote some kind of parameter to label, dimensionless parameter to label to go with your different orders. This is just labeling. Okay. Okay. So this is a perturbation approach. Yep. So what you do is you put this to the equations, and you expand it according to their perturbation order. You group in them according to this small number. So what will happen is the 0th order will have everything 0, right? So E1, E2, 0, E2, EP 0, E3, EP 0, right? E1, E3, E2. Oh, sorry. So I'm just gonna write the cross term down. Right? Now, since we don't have any field to start with, our initial condition is 0, right? We don't have any field to start with. So actually all of them are 0. Okay? Because no field except for one, we do have this. We do have this, right? We do have this initially. So all the cross terms are 0 because we don't have field to start with. The square terms, this is also 0, this is also 0, right? We have this that is non-zero. Okay. Will this do anything to my field amplitude? Let's see. This. So since we are assuming this as external drive, it's non-depleted, so we're gonna ignore its dynamics. We're just gonna assume that this is, so P is just KP WP. It's just this, right? EP0. This is EP square to, I forgot we delete the K term. So let's just focus on the temporal dependence. 2P, right? Of course, with conjugates. Now, this is a time-dependent term. So after the second derivation, it's something like this, times some kind of a coefficient, right? So now you have this term times a coefficient times a drive that is oscillating at 2 omega p. If you have a harmonic oscillator that is resonant at omega 1, okay, and you're driving it at omega p, which is a higher frequency, much higher frequency, will you do anything to the harmonic oscillator? Can you excite it? Can you excite it? Well, it can drive it, but not excite it. By excite, I mean resonantly driving. Okay, so the field does follow it, right? Remember that harmonic oscillator, when you have an off-resonant drive, it does follow it. But the energy doesn't really go into the system. It does not accumulate. that energy. So so that ignore the damping part. When you have a harmonic oscillator and you have a resonant drive, when the drive stop, the harmonic oscillator continue to oscillate, right? But if you have a non-resonant drive, so you give a pulse and the drive is non-resonant, it will follow your drive as long as the pulse is there, but when the pulse is gone, it will stop. Okay, so the trajectory goes like this. So this is the resonant drive. So this is your pulse. Okay, your pulse, when the pulse is gone, it continues to oscillate. But if it's off resonant, the drive goes like this. It goes like this. When the pulse is gone, the oscillation also ceases. Sorry, this I should label this differently. So this is the pulse, this is the pulse, and this is the trajectory of the harmonic oscillator. Okay, so a non-resonant drive does not put energy in to the system. And that's why I call it, it's not exciting it. So you can see that this omega 1 and this drive frequency 2 omega p are very different. 2 omega p is very high, at least 2 or 3 times higher than omega 1. So actually, at least 4 times higher than omega 1. So it will not drive it resonantly. Okay, so this won't do anything. Okay, so this is 0 because it's non-resonant. No, it's not 0, sorry. We are gonna discard this because it's non-resonant. It's not gonna do anything. And we discard this because the initial condition is 0. They're discarded for different reasons. Okay, it's important to keep that in mind. Okay, how about the first order term? The first order term is more interesting. Okay, still the same. The homogeneous part is the same. Sorry. Here's a square. Now, because this has this in front, right? In order to match it, you need to have a 0 and a 1. Yes? So the drive will match in terms of order of magnitude, will match with the homogeneous part. So you need to combine a 0 order and a first order. Okay? And again, so this is 0, non-resonant. And again, all the zeros are okay, let me just do this. So there's actually a lot of combinations. And there's no 1 for the pump. The pump only have 0 order, right? Remember? So with the pump, you do this. Yeah? And the square turns. And the square turns, you can have this. Okay? But again, anything involved with the 0 is 0. And you don't have, yeah. Anyway. So basically you have this 6 turns. 3 turns. That is eligible to be put here. This is, of course, 0. There's also this one. They're both 0, right? So basically, you can see that what is remaining, what is not eliminated by the initial condition is terms like this. And these are the key terms. Okay? These are the key terms. Let's see. Oh, actually, I'm sorry. Let me. We have a little problem here. Let's see. I need to use this term. Okay. Okay. Oh, I see. I'm sorry. There's another, this is wrong. My bad. I'm sorry. This is a small term. This is a small number. This is also a small number. So this shouldn't appear here because this has the same, this kind of accounts for 1 of this chi. Because this is already a small number, so this is, even if you use this is the first order term. This is counted as the first order term. Okay? So, I'm sorry. So this is the first order term. So it shouldn't even be, oh. Okay. Sorry. It can be there because this is, although this is the first order, this is the first order term, this is the first order term overall. This is the smallest term you can have from this bracket. So that is the 0. That is like the least you can have. So it's okay to put it here. But now when it comes to here, this is 1 chi, and so all these terms with the first order in it, it has a chi in it, right? So together they are the second order term. Okay, so you can actually, we shouldn't even write it here. It cannot be. This does not match with this. So they shouldn't be here. But the 0, 0. Let's come back to this. The 0, 0, they can. I'm sorry, this is, I know this is confusing. Let me just rewrite this. I was wrong. My bad. We cannot match it because this is the, yeah, we just cannot match it because the order of magnitude doesn't match. Let's do it again. This time I'll do it fast. I'm sorry if this math is very cumbersome. I'm already trying to do as least as I can. All right, So this is the zero order. Since this is working as a chi, we don't have anything here. Okay. So let's just get that clear. And now we directly go to the first order. First order has a chi. First order has a chi. Okay? Now, which term are you allowed? So in the perturbation approach, which term are you allowed to put here? Since this is working as a chi already, it matches with this. Here you only can have the zero order terms. Okay? So let me write again. And this will bring us to a very nice point on spontaneous parametric down conversion. This mechanism I am explaining to you is called parametric down conversion or parametric excitation. But in the experiment, we have the spontaneous parametric down conversion, right? Where does that come from? I'll tell you in a moment. 2. So this is 0. This is 0. Actually, E1, E2. Okay. So we also have the square terms. I'm going to write all of them out. Okay. So basically, all of them are the possible combination we can have here, regardless of the initial condition. Okay, so these are the all possible combination we have according to the perturbation orders. These are the zero order times a small number that matches with this. Okay, good. Now here's a key point. We know that, so regardless of the initial condition, this will give a term that is omega 1 t, and this will give a term that is plus minus, actually, plus minus, right? So combining this, you will have, yeah, nonlinear optics is very tedious, but it's very interesting. It has very, very many interesting phenomena, but the math is very tedious. So this can have two frequencies, right? This combination can produce two frequencies, the sum and the difference. Each one of them have the sum and the difference. Yes? Good. Here you have the difference. Sum is 2 omega 1. The difference is 0. Okay, so this doesn't do anything because this is, anyway, the difference doesn't read, it's non-resonant. So it's not going to do anything. Okay? So here you have plus, you have minus, and here you have this. Here you have this. Here you have this. Okay, good. We don't need to worry about the zeros. The zero frequency is DC, and it's not going to be resonant anyway. The second harmonic is not going to be resonant here either. So I delete them because I disregard them because they are non-resonant. Okay. This, of course, cannot be resonant because this is detuning from the resonant frequency up and detuning from the resonant frequency down. Okay. So all of them are non-resonant. Okay. Now the interesting thing is, can this be resonant? Can this possibly be resonant? This is where the parametric excitation comes from. Okay? parametric kind of refers to this mixing process, and this is the wave mixing thing I was talking about. Oh, I erased it. This is wave mixing. So can this omega 1 plus omega p be resonant? No, this is detuning up, right? Omega 1 up. So this cannot be resonant. Omega 1 minus p cannot do, right? Can this two do? This turn, omega p is here, so presumably you have two lower frequencies, right? 1, 2, and p. P is higher. So this is p times another frequency up. So p is already above your resonant frequency, and times another frequency that is even higher. So this is also non-resonant, right? What's left is this. Okay. Can the difference between 2 and 1 and p equal to 1, or to be, because this is a bigger number, so let's just do p minus 2. Can this equal to that? Yes, it's possible. It's possible, right? It's possible. So we're going to keep that term. By the way, so this is a small number, but this is only for labeling. At the end, you can equal all of them to 1 to erase it, okay? But I'm just going to put it here for now. So this is the combination. Okay. So this can possibly give us an excitation. But like I said earlier, we had a problem with the initial condition. The zero order, right? This depends on the zero order solution. If initially you have 0, then the zero order is not going to do anything. Yes? Therefore, in order for parametric excitation to work, there needs to be, if you want to produce 1, there needs to be another input, 2, in order to produce 1. Yes? Actually, it's more like this. Because you can write the same equation for 2. And as you might expect, for that equation, the resonant drive let's see, 2. For that equation, the resonant drive is the combination of E1, EP. Yes? It's symmetrical. So this together give that, and this, this together give this. Okay. So if you don't have any input on 1, you cannot produce, you cannot excite omega 2. If you don't have any input on 2, omega 2, you cannot produce omega 1. Okay, so this is the parametric process. So in optics experiment, if you want to, it's actually a three-wave mixing. If you want to produce this color, you need to put in 2 colors, and then this beam will, so part of it will mix it with that and produce omega 2, and the remaining of that will stay in this bin line. Okay, so that this is basically how it works. This. Yep. So okay, so this is all very cool, very complex. But what's the point here? What does it have to do with our experiment? Why go through so much trouble? Because this is gonna make our life much easier in the next 30 minutes. Okay, now we have to establish this, right? You need input. So you need input in order for this thing to work out. All this trouble is just to show you that term, okay? You need input in order for it to work out. The input can come from another laser, or it can come from the vacuum field. Right? Remember the vacuum photon. The vacuum field has non-zero fluctuation in terms of field amplitude. Its field is 0, but in terms of field amplitude, it's non-zero. And that is sufficient to give that spontaneous moment of field fluctuation is enough to facilitate this process. So the vacuum photon remains the vacuum photon, but this, so spontaneous, that's where the name comes from. Spontaneous parametric down conversion. Okay, this vacuum turn mix with P, and P breaks, well, actually, it requires 2 vacuum turns. The P breaks into, so in this process, the vacuum turn remain vacuum, but omega 2 is excited, right? And so that's this process. And in this process, omega 2 is mixed with omega P, so the vacuum photon remain vacuum photon. Is not, it's like a catalyst. It does not participate into the chemical reaction, but it helps it. Yeah? So the vacuum photon helps the process, help this to excite omega 1. Okay? But it's not participating in the reaction, so it leaves intact. Okay? But these 2 processes are symmetrical. They're conjugated. When you have equation for 1, you must have also equation for 2, right? So this is like a pair. So okay, so that's how it works. So this So this vacuum photons we don't see. What is observed is this breaks into 2 and 1. That's how it works. Okay, that's why it's called spontaneous, because the spontaneous depends on the vacuum fluctuation. You don't know when it's gonna go up, I mean the field amplitude, you don't know that. But at an instant moment, instantaneously it will go up and fluctuate. And overall the field amplitude width is 0, but the mean is 0, but the amplitude is non-zero. Okay? But at each instance, the field amplitude can still be of some value. It's just like the overall overall over time the average is 0. Okay. All right. So this is the vacuum, or you can call it vacuum induced or vacuum assisted parametric down conversion. Okay. All right. So these are all. So this part is in classical optics, classical electromagnetism, right? Everything I wrote here is from Maxwell equation, and it all depends on the input, right? Input must not be 0. This vacuum thing, this is from quantum optics. It is the vacuum fluctuation is the quantum feature. Okay, so the fact that you can have no input light, but a generation of 2 photons from the single pump light without any without an additional source, that fact by itself shows you that there is vacuum mode in your surroundings. You just cannot see it. Ooh. Okay. Okay, so that is the quantum feature of it. All right. Now, I have 20 minutes remains, and what I want to do is to cover single mode squeezing. Okay, now we have this foundation. It will not be hard to discuss what single mode squeezing is. Okay, now I want to switch. I want to switch to the quantum picture. Now I'll switch to the quantum picture. Remember? Okay. Let me take one step back. So I told you that earlier we have E equal to 1. It could be 1 feet. So that is single mole, and this is 2 mole, right? Okay. I wanna. So after we have explained this, I want to discuss the simplest case, the degenerate case. So in this case, this P just breaks into 2 mode that are two photons that are of the same frequency, that are of the same mode. Okay. So let's discuss this because the quantum treatment is simpler. Okay. So in the previous lecture we have talked about the Hamiltonian of electromagnetic field. Yes? Do you remember what that is?
Minus IH plus P hat divided by T.
Okay, it's this. Right? That's the vacuum. Sorry, that's the field Hamiltonian. Now, and this comes from EP, E and B, right? When the field is interacting with the media, with the material, the interaction term is this. This is the dipole or induced dipole, and this is the field that is corresponding to this. Oh, sorry. No, sorry, this is the total field. So whatever field that is. Okay? And from our so this D is the same as our P earlier. We just use a different notation here in quantum. This D is it's basically this. Yeah? Okay. So from our previous discussion, all of them will come in. And now we are considering E as E1 and EP, right? And you can probably see that not all of this term will be effective in terms of driving and excitation. Okay, what will be effective is this. This is what will be effective. Okay? Now, this is the field here. So this is 0. So together, they give there's probably some constant in front, but we don't worry about it for now. EP. Okay? So together they are like this. And we know that here, on your screen, I want to use black. Okay, so in this condensation process, after we find out about the operator, if we redo the math again with this knowledge, you'll find that this is this, and B is this. This is very much like the real part and the imaginary part. Okay? So this is the operator. Okay. So basically we have that. Okay. And this we will keep as because it's not depleted. There's this thing called parametric approximation in quantum optics. Approximation. I mean, formally you have to do this, but the parametric approximation assumes your field is in a coherent state. So alpha is in the coherent state. And coherent state is an eigenstate, it's not depleted. it will not be depleted by the lowering operator, right? Okay, and with the raising operator, it will change a bit, but the approximation is such that we just ignored it. So this is exact, but the approximation is here. This is, we just treat this as that. Okay? So this is the parametric approximation. Right? So basically, this can be replaced. All the operators in this field can be replaced by a number with the temporal dependence. Okay? So together, this will become this and with some kind of coefficient in front. And this and that. Okay? So the parametric approximation basically just treat this E, which is here inside this dipole operator, treat this E as a classical field, a drive. It's very much like the drive in the Rabi model. Okay, and you have this. Now, there are different combinations. Okay, there are different combinations. And if you are like me, very bored in the middle of the night and you want to pick up your pen and then do a 20-page long calculation, then you will find that at the end of the road, you will find that these are not resonant terms. Okay, only these two will be resonant. Okay. The quick way to explain this is, and this is like a 30-second version. If we switch this to the interaction picture and illuminate and erase these terms, then all the operator will have a frequency attached to it. Basically like this. Okay? And these terms will have the frequency cancel each other, right? And what is left is this. And this cannot drive the system resonantly because the system now does not have, in the interaction picture, the system now does not have a homogeneous part. So the resonant frequency is 0. Okay, so when you have an oscillating term like this, it does not drive it. But here, you will get terms like this, right? And then this combined with this frequency, they will cancel each other. So all the oscillating temporal dependence will be gone. And this will resonantly drive the system. Okay? So this is what is important. Okay, so so with a 50-second explanation, we are left with these two terms. We throw away. So see, in quantum optics, it is the same. In quantum nonlinear optics, it is the same as the classical nonlinear optics. You need to look for the resonant contribution. Otherwise, there are so many terms. And basically, the thunderdbolt rule is that you need to either cancel the frequency completely or cancel it to just the right amount so that the remaining frequency is resonating with the system, depending on which equation you use. Okay? But let me just write this square. So after the cancellation, blah, 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 you can, okay. Let me just keep it in its original form. Okay. So we are left with this. Okay, and then, so this is the original form. And if we do the interaction picture, blah, 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 then we will have, okay? And this cancel, this cancel. So you throw away a few more terms, and you're left with this. Okay? So this is the interaction picture, by the way. Okay, so now your photon Hamiltonian reduced to this effective form. And to see your revolution, the revolution of the field, because this is where the squeezing come from. Remember, we have the Schrödinger's equation, right? So in quantum optics, we still use Schrödinger's equation, except it's just that the Hamiltonian. Now, since we don't have a particle of mass, we have a particle without mass. It's a pure energy, right? So we don't write the momentum operator. It doesn't have that form anymore. It just have this general form of Hamiltonian, and whatever your Hamiltonian is, it goes to here, okay? And the evolution of the field, of the state, is basically this. Okay. And this is just a shorthand of a serial expansion of an operator. So you have the linear turn in H, the quadratic turns, the cube turn, okay, many turns. Okay, but let's write it as this. Oh, actually. Okay. Okay. The initial state that we're going to take is the vacuum state. So this will be the vacuum state. And this is an operator that works on the vacuum state. Okay. By the way, when you have lasers, it basically works the same way. The field, the interaction turn. Now this is the linear turn, and this is your pump field, right? And this is your target field, right? And the pump field here is not really a field. It's basically a current driven by the source. So anyway, this is a linearly induced dipole turn, and this oscillates at a certain frequency, and this will, by all this same math, it will go to here, except here you have a, not a square. You have a dagger instead of a dagger square, and that is, so you will have something like something very similar. something in this form. Let me just write alpha. Alpha something like this. Okay, and this will work on the vacuum too. Okay, so when you have like a current source that make a dipole, so not an induced dipole anymore, but like a real dipole. Okay, a real dipole that is driven by the source. That will give you this term. Okay, this is called the displacement operator. And this, when this term operate, when this operator operate on the vacuum, it gives you the coherent state. It gives you the coherent state that oscillate at the frequency that you drive it, of the frequency of the dipole. Okay, so that's basically dipole radiation. That's how dipole radiation works in quantum optics. So through the same math, through the same mechanism, you look for which one is the resonant one, and then you bring it in, and at the end, it will all come down to this, some kind of operator, a square a, like this, and they'll all work on the vacuum. Okay. This is this particular. So this is called the displacement operator. Displacement operator. And this is called the squeezing operator. And it will become clear what the displacement and squeezing comes from. It comes from the phase space representation. Okay, but just know that this is called the squeezing operator. All right. And how does that work mathematically? I will not show. But if you expand it, if you so I'm gonna just do this. Okay. So there's a coefficient. If you expand this, you have the linear term. You have high order terms, right? So the exponential expansion is, sorry, the exponential expansion is this. Am I right? Yeah. Yes? So if you have an operator there, you expand it the same way. You should do this, okay? So this is the mathematical recipe. I don't know why it works, but mathematicians prove that it works this way. For our convenience, everything have the same formality. Okay, now I want you to see that this will raise this to 2. This will raise this to 4 and 2. And this is 6, 4, and 2. You see that? Because we have the raising operator to the second order, the raising operator to the fourth order. This is the raising operator to sixth order, right? And every term is in unit of this, and this is an even order. So you only have 6, 4, 2. Okay, so basically, so 0, of course there's 0, there's a 0. So you can imagine that from this, the superposition state, you have some kind of coefficient, and you will only have the even numbers. Okay? So qualitatively, you can see that. And So this is your state that from the vacuum applying the squeezing operator or the parametric process, you have this, and the photon. So the probability distribution in each photon state is Cm squared, right? And this only take value at even numbers. So 0, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah? So this only take value here, 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 here. Okay? And as you can expect, so there are some kind of coefficient in front, right? So with each order, you have the coefficient, the small number coefficient at a higher order. So that means the probability from this, the probability, whatever amplitude that is contributing to this, is gonna be small, right? So 6 appears here, start to appear here. Fourth, 2 already. What I'm trying to say is, you see, all these terms contribute to 2. All these two terms contribute to 4, right? And this appeared only here for the first time. So when you do just expansion to a third order, you already have 6, and you know this is going to be small, and they are, yeah. It's not hard to understand. It's going to go like this, and 0, everybody had 0, right? So it's going to go like this. This will turn out to be some kind of exponential. Let me just write beta. Some kind of exponential trend. Okay. This is the squeezing state. This is the vacuum, the so-called vacuum squeeze, because we're starting with a vacuum state, right? So it's called a vacuum squeeze state. Vacuum squeezed state. Okay? Vacuum squeezed state. All right, it has this train. Now, remember I told you that the coherent state has a Poisson distribution, right? It goes like this. And this takes even and odd numbers. Okay, so this is the coherent state. This is called the squeezing state. I just want to say that this is the coherent state. And the coherent state here is generated with the displacement operator. Okay, so you see that the operator, when they have different orders in E, they generate different the photon distribution has different characteristics. Yes? Okay? So this difference in the photon distribution can only be seen by the second order correlation measurement. So you see it's all coming together. Yeah? When you have nonlinear generations, it will necessarily involve nonlinear, like higher order A, right? And that will give you a different photon characteristics. So if you generate any light from a like second harmonic generation, whatever, any nonlinear process that generates light will necessarily have a different photon characteristic, different photon distribution than the coherent state, because this is generated from the first order process. but without using the second order coherence measurement, the second order, yeah, the correlation measurement, we cannot see the difference between these two. Okay? So just coming back to, like how do we see the quantum coherence? The quantum coherence is here. Yep. Okay. Now, last remark is, okay, we have already exceeded our 90-minute limit, but I want to, actually, I want to continue. I want to just have another 10 minutes. I just want to have another 10 minutes to finish this lecture. So the next time I can come back to the MV Center lecture, quantum spin lecture. Okay. Remember that I said that the field Hamiltonian is very much like the oscillator Hamiltonian, right? It's very much like oscillator Hamiltonian. This is the field, and the oscillator is I'm just going to use different color. I'm not going to use this different notation. So this is particle. This is particle oscillator. Okay, and this is field oscillator. Yeah. All right. So I told you that they're very similar, right? This has another form. Right? It is possible to write this also in this notation. I'm going to put 0 here. It is possible to write this also in this notation. Q square and P. Okay? It is possible to define a similar, so there is a relationship between the X and P operator and the A and A dagger, right? It is possible to define another linear combination in terms of A and A dagger here, so that this has another form like this. Okay, so this will resemble the particle harmonic oscillator, except that the mass here is 1. Okay, but don't take it literally, because we really don't have it's not a photon. Okay, so don't take it literally. We don't have anything with a mass of 1. This is just formally we can define a linear combination of Q and P. Actually, let me just write it down. Q is yeah, Q is this, and oh no, Okay. Okay, so it's possible to define operator like this. Okay. Now, if you make this operator dimensionless, okay, so this is H. Okay, forget about it. If you make it dimensionless, okay. If you make it dimensionless like this, so you take out the units, you end up with this x1 and x2. They are called quadrature. Not sure how to spell it. Quadrature operator. Okay? Quadrature operators. And why do I want to bring it up? Because the quadrature operator is basically the E and P operator. Okay. So it can be shown. So like this is where the connection comes from. The quadrature operator is the dimensionless E and B operator. So with the proper dimension, everything you put everything back, then this will give you the E squared. Oh, sorry. And the B squared. Okay? So that's how all this is connected. So basically, E and B play the role of position. Okay? This is E, this is B. This is position, this is momentum. So E and B play the role of position and momentum as in a particle oscillator. Yeah? And the reason I want to bring this up is because I want to introduce you to this thing called phase space and the phase space probability distribution. Okay, so you probably have seen this diagram. So in your if you're a physics major and you take classical mechanics, you probably have seen this diagram with X here and P here, and then you can see a harmonic oscillator going in a circle. Its trajectory goes like in a circle, right? The reason we want to draw this picture is because this represents all the possible state of the oscillator, since X and P are the only two dynamical variable of the operator. Whatever X and P value it takes, the oscillator will be on like one point in this map, right? So this is representative of the full state of an oscillator. And if you have an oscillator that is oscillating, then its energy is constant, and that is shown by a circle with a fixed radius, with the radius representing corresponding to its energy. Yeah? Great. And if you have a driven oscillator, then it will go from, the trajectory will go from like this. The radius will grow, a resonantly driven oscillator. If you have a damped oscillator, it will spiral down. Yeah? Okay, so this is a very useful picture for single mode oscillator. No, sorry, for single frequency, for just for one oscillator. Okay? It's a very useful picture. Now, if you're dealing with not a clean system, you have dealing with an oscillator in a noisy environment. So it's constantly driven and damping, right? Its value will not be like this, but it will jump all over the place. Jump. Basically, it will look like this. An oscillator in the noisy environment. When the fluctuation and dissipation both working on the oscillator, actually they have to work together because of this fluctuation dissipation theorem. But basically they will look like, the trajectory, they will not be, it's kind of a random walk in a two-dimensional space. Yeah? So this also can be used to visualize the dynamics of a very noisy, an oscillator subject to noise. Okay. And this radius basically has to do with your thermal temperature. Okay. Good. And you can, as we know, the Boltzmann distribution is this, right? So it takes all possible energies, and they distribute it with the certain width, right? So each energy are possible for this this oscillator for a brief moment. This is the lifetime. You can see this like the lifetime, the lifespan of the oscillator in this energy, and this is the lifespan of the oscillator in that energy, right? So these are like circles, different circles. And the oscillator jump from one circle to the other circle to the other circle, and the chance of it being in the outermost circle is the smallest, and the chance of it being in the innermost circle is the highest, right? And the radius, this is kT. That's why I say this disk is approximately kT. But if you just record its state is, so it's state. So this is its state, right? If you record its state as a function of time, and record it for a long time, you will see basically a 2D distribution, a 2D Gaussian distribution here, or it doesn't have to be a Gaussian shape. Maybe a 2D shape like this. Anyway, it will be a bump. So that 2D function is a probability distribution of x and p. Okay? And it is possible to just use this function to study the dynamics of an oscillator instead of Newton's equation. It is possible to just, like, I do not want to know my trajectory. I want to know like how likely I can find my particle in certain state. I want to see how this evolves. And this the equation that evolved this is called the, I believe, Liouville equation. Okay, it has another name to it. But basically that is just another representation of the Newtonian mechanics. All right, why do I mention this? Because we can do exactly the same thing for the field oscillator, except here we will not use x and p. We'll use the quadratures. Okay, we'll use the quadrature values, and the vacuum state looks like this. So if you, because the quadrature resembles, is basically E and B. is like a dimensionless EMB, okay? A vacuum state will give you, so if you measure the field amplitude of the vacuum state at different times, you give you this. Very much like a thermally driven harmonic oscillator, it will give you this. And this will be a Gaussian. This will be a Gaussian distribution. Yeah, and this is called the vacuum state. And all the so all the information of a state that is contained in the amplitude, the eigenstate amplitudes are also here. Okay, they are also here, including the photon this photon distribution. They can also be visualized here. Okay, and this is the average. This is the energy. This is also the energy, but in this case will be the photon number or the intensity of the field, which is the photon number. So I was just gonna write I, and this is the photon number. Okay. So this is the vacuum state. The vacuum state. So one axis is B, one axis is E. Okay, and if you look at E, if you look at the projection of E as a function of time, it will go like this. Okay, this is a function of time. This is x1 or E. It will go like this. The field in average has a 0 value, but the amplitude is not 0. Okay, this is the trajectory. This is the field trajectory of a vacuum state. Okay. Now it becomes interesting. In this picture, it becomes very interesting to discuss how the field look like in different photon distributions, right? Because all this information that is contained in the probability amplitude can be cast to this form. And by the way, the quantum, and this is also valid for quantum oscillators. Okay, so but here for quantum field oscillators, the probability distribution is called Wigner function. Wigner, it has a name. This is like a Leo view, and this is Wigner function. And the funny thing is the Wigner function, unlike the classical probability amplitude, this is not the real probability amplitude. It's called the quasi-probability amplitude because it can take negative values. Okay, all this Leo view probability to the phase space probability only take positive value, and the positive values are the counts, right? These are the counts of your oscillator being in this state how many times, or for how long. But Wigner function, the field, the state can take a negative value in the Wigner function. And that is defined as the non-classicality of the field. Okay, so the non-classical, the quantum nature of electromagnetic field is shown, is manifested in the negative value of the Wigner function. Okay, I'm not gonna go into the detail on how we calculate the Wigner function. It's on the book of Knight and Gary and Knight. So that's a great book, into quantum optics and introduction. So I highly recommend it. They have a lot of beautiful pictures of different states in Wigner function, and also the field trajectories for corresponding to different states. Okay, I highly recommend it. But my point, what I want to make is the negative value of the Wigner function, which will not. So you can say the negative value in the quasi-probability quasi-probability function is a smoking gun for the quantum light. Okay? So quantum light or the quantum nature will have these characteristics. Yeah? So yes, the second order correlation measurement is a nice way to show the difference between this and that, to show the difference between the photon distributions. But the true quantumness really is in the negative value in the quasi-probability distribution. Okay? So, okay, let me just say a few more words about coherent state. So for a coherent state, so it's all out. Coherent state. I'm probably not going to cover this too. I don't have time. But for coherent state, the probability, the Wigner function is like this. It's a Gaussian bomb sitting at a distant way from the origin. Okay, and it circles this phase space like this. Yeah. So the Gaussian function, it takes only positive values, and it circles. So the field that it traces out. So this is. So this is this, right? And then as it goes, so if you go this way, as it goes, so the field it traces out is this. With the width. I'm doing a very bad job drawing this, but basically you can see this is basically the size of this ball, and as the ball goes through the circle, its projection on here goes like this, right? Okay? This is the uncertainty of the field, called the shot noise. Whenever you measure the field, okay, no matter how precise your element and how quality your element is, there exists a fundamental noise or field distribution or field errors. That's called the shot noise. And that shot noise is from the vacuum state. The origin of that shot noise is from the vacuum state. Okay? So the displacement operator take this whole blob, this Gaussian blob, and displace it in this phase space by this certain amount. That's why it's called displacement operator. Okay? And then it circles like this. And that shot noise just the noise from the vacuum field just goes with it. Okay? Now, the squeeze state. What does the squeeze state look like? See, this is to explain what squeezing means. It's necessary to introduce the phase space representation and the Wigner function. Okay, the squeeze state looks like this. Oh, by the way, okay, I'm going to give you one quick tip. So if you imagine this is the harmonic oscillator, right? And you have this thing here. By the way, the projection of the Wigner function on each axis is the corresponding probability amplitude. So So this is the very special quantity. So if you integrate it along one of the dimensions, these become the probabilities in the projected. And this is the same way here with the other axis. Okay? Okay. So now we can look at this. So this is the probability amplitude, right? So this is the probability amplitude. No, sorry, this is the probability. Right. Remember I told you that the interaction Hamiltonian for displacement operator involve only one E, right? And E is like X, correct? So this is almost like you have P. So this is, okay, let me just use this. So this is the drive, right? This is almost like changing the frequency. Sorry, not changing the frequency. How does this work? Anyway, what I want to say is it should produce some turn like this, some kind of turn like this. And this is like displacing the operator, displacing the harmonic potential. So like you displace it. That's why it's called displacement operator. So the function of that is like displace your unperturbed potential, so that this vacuum field remains the same, and then but now it's not sitting at the bottom, right? So in the new potential, it's on a non-equilibrium position, and it will start to slide back and forth. So that's like this. So you displace the potential so that it starts to oscillate. That's why it's called displacement. Displacement. Okay. Here, for squeezing, you can play the same game. And so you can play the same game and ask what is happening to the what's the equivalent picture for the unperturbed potential. And since it has the a square term, so basically E squared, so X square term. That's basically change. Oh, all right. Oh, yes. Okay, I now remember. Sorry. This is X, right? This is X squared. Okay. The displacement is a linear term, and the linear term combined with the potential, it becomes a displacement. Yeah? Now here you also you have a square term, right? And the square term combined with this potential become a different frequency. Yes? So the effect of this parametric drive is to change its frequency, and to change its frequency means to change the form, to make it narrow, like this. Yeah? To make it narrow like this. But this is a time dependent, but this oscillates with time, right? So this, for one instance, it make it narrow. For the other instance, it make it loose. So up and or down. Up, down, up, down, up, down. This is a time dependent, right? Or there's a cosine term attached to it, okay? So this is time dependent. So it's up, down, up, down, up, down. So what happened to the vacuum state is that for a moment it will get squeezed, and the other it will get loosed. So you get squeezed in one side, and on the other moment it will get, so it becomes like this. Okay, it becomes an oval. It goes from a circle, from a disk to an oval. This is the vacuum squeezed state. You see that it's squeezed because of this pinch. It's like squeezing. But this happens in different times. So as this disk rotates, right, just like this will rotate, it kind of squeeze it in one direction and stretch it in the other direction. So that's where the name comes from. And the field trajectory looks like this. When you are like this, your projection is small, right? When you are rotated like this, your projection is big. It's all centered at 0, though. So it goes like this. That's your field. Like this. That's the vacuum squeezed state. Okay? And because here we'll only talk about one oscillator, one frequency. So that's one mode, right? Remember, mode correspond to K and polarization, right? And yeah. So this is single mode squeeze state. It looks like this. And it has the forward distribution that is on the R state. Okay? Great. I'm done with this. The rest will be fast. I say I wouldn't discuss it, but I will now. I changed my mind. Oh, because I really want to finish it. I should have given this full lecture in one lecture, but later I found that it's too long, so I break it into 2, and then now it becomes 3, and I don't want it to grow indefinitely. So 10. So 2-mode squeezing, what's the deal with that? So instead of a single oscillator, we have 2 oscillators, okay? And the Hamiltonian looks like this. A, B, and you have A, B, and A, B. Okay? So it looks like this. 2 oscillator. The coupling term, instead of A square, it breaks into 2. Okay, so after our discussion with the classical Maxwell's equation, it's not hard to see that this is how it will work out. Okay, so we're not gonna bother with the math anymore, since we already spent enough time there. But what the time we spent was just to give you a foundation to understand like why this is reasonable. So single mode break to 2 modes. Okay, and and only this term is resonant. The rest are not. Okay, so it goes through the same argument. Okay, but now there's a very important difference between single mole. So this is 2 mole. 2 mole squeezing. So 2 mole. So instead of 1 mole, we have 2 mole. You see, in each element, in each the coupling or the squeezing operator is linear in each turn, in each field, in each oscillator, right? So if you expand it, so if you take this as the single mole squeezing operator, right? And then you work on the vacuum A field, the vacuum B field. This is the vacuum field of the 2 mode, right? If you work on this, so this is an exponential A, B, A dagger, B dagger. Oh, okay, actually, let me just use this notation. And like we did before, we can have the first order second order and the third order, okay? You see, once you understand the logic behind it, the math doesn't seem too hard. It's all the same. Okay, now this will act on this state, right? And what kind of state it will produce? It is possible, it is always a pair. Right? So 2. Wait, let me see. Right, 2. One. Okay, this is okay. There are more combinations here. I'm not gonna go into it. One important thing I want to point out is, you see, for single modes, not for single mode, for individual modes. For individual modes, it is possible to have 1 and 2 and 3 and 4 and 6. It's continuous. It's not even number anymore, right? So this is N, A, this is N, B, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Now it becomes like this. Instead of the even number, you can take both the odd and even number. Yes? The reason is now the pair production. Where's the pair? In the single mode, the pair is 2 photon in the same mode, right? So you always go 2, 4, 6, right? You always go even numbers in your excitation. But now the pair goes in 2 modes. So every time I produce a pair, but in each mode a single photon, in each mode a single photon, in each mode a single photon. So the pair is here. They are always the same. they are always the same. But individually, they can go from 1, 2, 3, 4, 5, 6, 7, 8. Okay? So this is continuous. This is not. So this is like this. So n from 1, 2, 3. Yeah? And the other mode is 1, 2, 3. Yes? Okay. So if you see this, then it won't be hard to understand the result of your, one of your experiment. When you block one beam and measure the other beam, and you try to see if there are single photons in it, right? You use a Humphrey-Brown twist HBT measurement, and you try to split that beam and see if it's a single photon beam, right? You don't see a single photon result because you're looking at this. It's not a single photon distribution. Okay, yeah. Oh, by the way, okay, so right. One thing I want to say is this width here depends on your pump. So this coupling coefficient depends on the pump. The harder you pump it, the broader it goes. Okay? And the reason we can use it as a single photon source is because we pump it weakly. We pump it weakly. So it basically goes like this. It kind of diminished at n equal to 2. So you either have 0, a lot of 0, or you have a little bit of 1. So it's 1 photon in one mode. But in principle, it could have 2 photon state in this mode and 2 photons stay in this mode, or 3 photons stay in this mode and 3 photons stay in this mode. And in that case, if you run a Humphrey-Brown, so if you have 2 photons stay in this mode, right, and you run a Humphrey-Brown there, you could potentially see. Oh, actually, no, the other way around. Sorry, the other way around. Let me just say it again. If we pump it very, 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 very weakly, so that this distribution kind of cut off at second, right? Then in each beam we have 0 and 1, 0 and 1, right? And in that case, if you run a Humphrey-Brown measurement on one beam, it is possible for you to see, the anti-correlation, the single photon result, the dip. It is possible. But the photon count rate will be like super, super low. And you have to accumulate your data for a very, very, very long time. Okay? So with the power that we operate, we have, photon count rate quite high, right? So we are operating in this region. So I correct what I said. So this is where we operate. We operate at a high power pump regime. That means in each beam you have 1 photon state, 2 photon state, 3 photon state, 4 photon state. You have many. If you have a continuous photon distribution, okay, and this is what you measured. So of course there you would not see a Humphrey-Brown dip. Instead, you will see something very close to a thermal distribution, because you see this is very much like a Boltzmann, right? So the result is similar to the result of your HBT measurement on a single beam without information from the other beam. that result is very similar to a thermal distribution, to the result of a thermal light, because this is what you measure. So 2 mole squeezing on the single beam is different from a single mole squeezing. The single mole squeezing is 0, 2, 4, 6. I'm not saying that for single moles, so this is single mole, and this is 2 mole. I'm not saying here, if you run HBT measurement, you will see an anti-correlation dip. I'm not saying that, but I'm just saying that this is different from thermal. This is very much like thermal. That's all I'm saying, okay? That's why the menu says that this, you will get, basically you get a thermal light result. But it is really not thermal light, because thermal light has effective temperature. So this width correspond to effective temperature. Sorry, this width correspond to the natural, the room temperature. That's the thermal light, okay? Oh, sorry. Well, it depends on the source, sorry. Depends on the thermal source. That temperature is dependent by the thermal source. But for us, this width is determined by our pump power, the blue light power. Yep. Okay. Lastly, so this is done. So lastly, we won't have lecture next week, because next week we'll switch groups, right? The optics will do the spin, and spin will do the optics. So next week we won't have any lecture. You have more time to do your experiment. So this is kind of making up for the next week. I'm justifying for myself. Okay.
So next week the optics group can make the first spin experiment.
Right. Yeah, but we will meet here first. We'll still meet here first, and then we'll walk to the lab together, because I'm gonna walk you guys through your respective experiment. So GRA experiment. Okay, so GRA stands for Hongji, Roger, and Aspect. I believe all 3 of them are French. And this guy just won the Nobel Prize a few years ago. And this experiment is the first experiment that demonstrates the single photon characteristic. So this dip, this correlation dip, okay? So this is tau, this is 0. So for all the experiment you have done so far, it's either 1 or that, right? This is a non-classical feature, because classical kind of stop here. This is the classical region. Okay, and here now underneath is the quantum region. Okay, so to demonstrate, by the way, the single photon state, or actually Fock state. So Fock state is any n. So any eigenstate of the field is called Fock state. So 2 photon state, 3 photon state, 4 photon state, they are all called Fock state. And of course, single photon is one particular example of it. And all of them, in the Wigner function, they have a ring-like structure. It's very funny. They go like this. They have, because this is number, photon number, and this is like the photon number uncertainty. Since the Fock state have a definite photon number, so it goes like a ring and with 0 uncertainty. Okay. Therefore, the projected field, the projective. But this has, so depending on how many photon you have, like 1 photon or 2 photon or 3 photon, the ring kind of oscillates. So I believe for 3 photon state it goes like this. So like 3 stripes. Yeah. It is just a very funny distribution. You don't get to see this unless you do quantum tomography. Okay, you can see that if you do quantum tomography, but not with the correlation measurement. But anyway, I want to come back to this. So they are the first one who demonstrate the single photon state, and they have major by how they demonstrate the single photon state. They demonstrate a quantum anti-correlation in the correlation measurement, and here's how they do it. They take an atom, and the atom has two transitions. So they somehow excite it, and there are. So this is the excited state, and this is there's a big jump, and this is fast. And then followed by it, there's a small jump. This energy is somewhere around 6 nanometer. So almost like X-ray, okay? And here, this is, I believe this is something like 600 or so, I forgot. But this is visible. So these two are two very different frequency, and they are emitted in the fluorescence way, in all directions. So all directions. They take 60 nanosecond photon as a trigger to trigger a detector here to open. Okay. So they have a beam splitter. They have beam splitter like this, and the beam splitter, and this is supposed to accept only. So they have filters in front, and this is to accept only 600 nanometer. So they have a filter in front. Okay, and they do a little Humphrey Brown setup here. And this, when they take this, when they receive a signal from the 60 nanometer, it kind of turn on the power, per se. They turn on the power of these two detectors, and then they are now active. They are now open to receive photons, and then they see if during this moment, like a certain time after the trigger, like it may be a few nanoseconds window, this will trigger a few nanometers, maybe like, I don't know, 5 nanometer or so. During this window, this are open for detection, and then they detect this. So you see, this light is now produced by a very different mechanism. Not parametric excitation. There's no pump light. It is just fluorescence. And since we know that atomic levels are discrete, and when they jump, it will only emit one photon, you can almost be sure. It's kind of trivial, but nevertheless, it's a demonstration, so it's cool. But you can almost be sure that this will be single photon source, because it is just between two levels. Okay. So it doesn't have a distribution like that. It basically has a distribution like this. This is 1, and that's all. Yeah. Okay. So here, they use this trigger to turn on the two detectors, and since the photon cannot be absorbed by two, it cannot be split. So you see this. Okay, so this is called a GR experiment. Now this is not tricky. This is kind of trivial. This is not tricky at all. What is tricky is the experiment that you do. Do I see tears? I mean, do I see tears in your face? Well, the experiment you do is tricky. I mean, it is not tricky on the menu, but it is actually tricky if you think about it. That's why I want you to write a report, write a report, because when you write a report and you think about your data, you really start to think. Okay, in your experiment, you are asked, so you're first asked to pump the BBO, and then tubing will come out, and then supposedly there are a detector here, and there is a bin splitter here, and there are two detectors behind it. Okay, so supposedly this bin goes to there, and this bin goes to there. Yeah, but now, and it has nothing to do with collapsing wave functions. It's not that mysterious. Suppose you don't use this trigger. You just turn it off. Okay, it doesn't matter if you collapse it or detect it. It doesn't matter. You can turn it on, but you just not feed the information to here. You don't use the information of the T detector to gate this, right? Okay, so actually, you know what? Let me just make it less mysterious. So suppose you have this all on, all of them on, but so this is the correlator, right? This is the correlator, and suppose this is the trigger, right? And now you break this, you don't connect it, okay? So you still can see photons on your computers. So say all of them goes to your computers. You have 3 trays, yeah? All of them are on, but here you don't use it to trigger the correlation box. So you just keep them on. Now what you measure here is the single beam. So this is mode A, this is mode B. Sorry, the other way around. This is mode A, this is mode B. So you are measuring single beam correlation. And since this beam has a photon distribution very much like the thermal light, you're measuring the correlation of a thermal, like that of a thermal light. Okay, we already talked about that. Now, what's next is suppose we use the information from the other one to trigger it. What happened? Well, first of all, we know the other one looks like this too. That's what the two mode squeezing tells us, right? The other mode looks also like a thermal light. Yeah? So in principle, you can detect 1 photon, 2 photons, 3 photons, 5 photons. Yes? Now, suppose you detect, at this instant, you detect, so this is 0, 1, 2, 3. You detect a 3 photon state. It produces a spike. And you use that to trigger here, open, right? At this instance, because of this pair correlation, you can be sure at this instance you will also have a 3 photon state. So a 3 photon state here will give you also a 3 photon state here. If you don't have that trigger, you don't know when you have the 2 photon, 3 photon, or 4 photon, 1 photon. You don't know. Every time, when it breaks, it can generate 1, 1, or 2, 2, or 3, 3. You're always in pair, but the photon numbers is uncertain. That's why you have these probabilities. You don't know which one is going to land on, right? So suppose you have 3. And if you use that as trigger, you can be sure that at this moment you also have 3 on the other side. Can this give you a non-zero result? A non-zero correlation? Of course it can. This is the 3 photon state, right? So you can have 2 here, you can have 1 here, right? And that will give you already a non-zero correlation. Yes? Suppose you have a 2 photon state, right? You can have 0 here and 2 here, or 1 here and 1 here, right? It will actually give you a pretty high. If it's 1, 1, it will give you a very high peak. Yeah. Actually, because of quantum interference, it will work out that it will be 2. Yeah, I wonder. Okay, let's just keep it simple. Let's not talk about the quantum optics of the beam splitter. Let's just say in the most general sense, all combinations are possible if this is a multi-photon state. All combinations are possible, and you're not necessarily going to measure a zero anticorrelation, right? But the fact that in your experiment, you actually measure anticorrelation, that is because I believe that is because we don't pump it strong enough. We pump it enough that it does not truncate at a second. So this is like really weak limit. Okay? And this is a strong limit. And I believe that we're pumping it at an intermediate region, so that in order to see this, it's very unlikely. You have to wait for a long time for this. The most probable, the dominant one is still this, single photon. So within the short time, if you have a short data acquisition time, like, what do I mean by short? 1 hour is short. 1 hour for one run. Most of you run like 10 seconds, 30 seconds, or maybe 10 minutes at the most. You're tired of it, right? That's for one run. But what I say, enough sufficient statistically means like 1 hour or 2 hour data acquisition time. That is the level of data acquisition time you need to have when you're dealing with single photon experiments. Okay, if you have enough time, I think it is possible that the dip here will be lifted up enough. It will probably be like this, and this is the contribution from the multi-photon state, 2 or 3 or 4. But because you're only measuring in a short time, so this dominates. So you have, for the short time, you have the dip. It corresponds to 0, perfect 0. Okay, so it's just a matter of the parameter that we choose to operate. That this setup happens to demonstrate the same effect that as the Hongji, Roger, and Aspect did. But our light source is completely different. Okay, so that's why it is a tricky experiment. A tricky experiment means that it only works in a certain parameter range. If we will use a much stronger pump, I'm sure this setup will not work. You cannot measure an anticorrelation with this setup. If we use a much stronger pump and accumulate our data for a much longer time, 2-3 hours. Okay. So that's it. Yep, that's it. Okay. So we finally are done with all our parametric thing. Okay, feel free to stand up because I'm going to do quiz, 2 quick quiz. And you can talk to each other, just relax a little bit, relax your legs. We're going to do quiz now. Quiz. How are you guys doing so far? How many did you do? Oh, you set your expectations. My lady. My second half of the semester. I don't think there's that much to lost count of.
Sorry?
I don't think there's that much lost count of.
It's one. It's just like if you some experiment doesn't matter. It's like two experiment in one experiment.
Okay. All right. So the first question for everyone is the expectation value of the electric field 0 for vacuum state? If you think yes, please stay on this aisle. If you think no, please stay on this aisle. Yes. Everybody vote for yes, or are you voting for no, Molly?
Is it perfect vacuum? Like, I mean, because it doesn't really exist, right?
It's a perfect vacuum state.
It's perfect?
Yes. How about you, Tim? Are you voting for no? I like that, by the way. If you're different from others, I like that. That means you're a fermion. You're not a boson. You guys are all bosons.
I think no, but I don't like to be different. Like,
Okay, you are a fermion who likes to be a boson. Okay, you think no, and you think yes.
Yeah, I think yes.
You all think yes. Okay. She doesn't like to argue. Why don't you? Or how about you? Why don't you convince her? Try to convince her. Why the answer is yes?
I'm not very sure.
Because she doesn't want to argue, so I'm gonna let you argue.
I think this one equal to 0, but this is not 0. Maybe.
Yeah, that's what the expectation value means. But
Yeah.
why? You need to explain to her.
I don't know why.
You need to you don't know why?
I don't know why.
You just memorize that?
Yeah.
Gosh.
He's gonna be a good engineer.
What? Are you sneaking to the other group?
I think I'm convinced.
Oh, wow. That easy, huh? Okay. He hasn't even say anything. All right. Actually, the answer is yes. Right. You're right. You'll go both right. You're both right. All right. Next question is. Now listen up. Osh. Is the expectation value of the electric field 0 for a squeeze state? Yes or no?
Is vacuum state the same as coherent?
No.
No.
Sorry, this is squeezed vacuum state. I missed one word. Squeezed vacuum state. So this is vacuum state, this is squeezed vacuum state. Do I have everyone on voting on yes? Okay, I'm gonna pick another one to try to convince me. Can you convince him why he should vote for yes? Even he already voted for yes. I'm asking you, Mark. I'm putting you on the spot. Give it a try. Come on, you're a physics major. You can do it. He's an engineering major. We pick on engineers in this class.
Yes.
Are you all physics?
No physics.
They're all physics.
They're all physics.
Yeah.
Not you.
Not me.
He's double E.
That's why he talks more.
Why?
No, because he's not just, yeah.
Why?
I'm less depressed. Mark, what are you doing? Are you playing with your phone?
Yes.
What the heck? Put down your chat GPT.
Okay, I'm trying to.
In my syllabus, I say generative AI is prohibited use in this classroom. Okay, don't let me see that again. You want to convince him? Oh, thank you so much. You want to use a pen?
The graph. I forgot the name for the graph. This thing, and then we have squeezed when it looks like this or this, and it oscillates between. And so if you draw the E over time, it looks like the thing you're drawing looks like. And then if we do integration over time, this cancels out this cancels out this, and so it goes at a 0.
Are you convinced, Mark?
That's my reason.
Do you feel convinced? Bioengineer? Are you convinced, Martin?
I mean, I just think there should be no electric fields in vacuums. So,
But this is squeezed vacuum.
yeah, but still.
I mean, the previous answer, yeah, vacuum, nothing, right? So no electric field. But squeezed vacuum is something you pump, and you can detect it with detectors.
But a vacuum is a vacuum.
But it's a squeezed vacuum.
If there is no particles or nothing, there can be no electric field.
Well, if there's nothing, you cannot detect it, right?
Yeah, that's weird. I don't get that.
Yeah. So why, if there's no expectation value, if the expectation of value of the electric field is 0, why can we detect it? Isn't that a great question?
Yeah.
I just came up with that. That's a third quiz. But no, that's not a third quiz.
Do you have an answer to that question?
Of course I do.
Okay.
Man, I'm the instructor of this course.
Maybe you just
How dare you
come
to
with
disrespect?
knowledge.
I'm just kidding. I'm just kidding.
Please give it though.
Okay, first of all, I think you're doing a great job. You're right. You're absolutely right. It is yes, and this is the reason for it, right? It's an oval shape in the phase space, so its projection on the E axis, as he rotates, it goes like this wobbly thing, and of course the expectation value is 0. Okay, that's cool. But now it comes back to our detector problem, right? So in the detector, if the expectation value is 0, how can a detector detect it? E squared, yes. But what does that mean? That's important. But what does E squared mean? Intensity. And intensity corresponds to?
The signal it detects is intensity instead of electric.
Energy, right? E squared corresponds to energy. Intensity is energy delivered per minute or per time per square, right? All the detections that we have used are based on energy. So even though the electric field is 0, if the energy is not 0, you still see it, right? You still can see it. So that just tells you that this detection process is fundamentally quantum mechanical. because this is the energy gap. And as long as you have an energy input that satisfies this, that matches with this gap, you have a detection. You don't need to drive it in the classical way, like a field. That's my answer. But you can say, I'm not convinced. I want to find out more about this question. And I highly encourage you to do that. And I just want to say, when it comes to a question like this, like how does our classical instrument operate with quantum principles, and how does that operation reveal interface with this quantum light? And when it comes to questions like that, most likely nobody have a definite answer, because this is still an active research field. Even though quantum optics has been existing for such a long time, and there are already several Nobel Prize awards to this field, but fundamental questions like this are still being explored, and people are still doing experiments trying to figure out like what the heck is going on. Okay, and the more we think about it, the more we ask questions, the more we understand what's going on. So quantum optics is actually pretty is pretty rich. You can never exhaust your questions. Okay, you can always come up with new questions that require deeper answers. And the more you dig, the more you find. Yeah, it's like a bottomless sea, vacuum sea. All right, thank you very much for your attention today. I know this is an unusually long lecture, but I'm glad that we have get rid of all our parametric related materials. And yeah, great.
Could you swing by the lab later?
Yeah.
You might have